Hello, welcome to the course UVC 001. In this module, we will see the applications of bipolar junction transistor as an amplifier. So, in general, for the amplification purpose, as you can recall that transistor has to work in the active region, and for the analysis of such type of circuits, two main segments have been required. So, first is small signal analysis, which mostly covers for the low frequency, and the second is large signal analysis, which mostly cover from mid to high frequency. The things will be clear with the respective frequency response. So in this particular course, we are limiting our discussion to the small signal analysis only. That means we will see later on the low frequency response. And for the understanding purpose, we are taking common emitter amplifier for the small signal analysis. So I'm taking a common emitter amplifier circuit, and in general, the possible models which we can use for this are basically three models. Number one is RE model, then hybrid model, or hybrid pi model. RE model, hybrid model, or hybrid pi model. So let me draw the circuit diagram first and we will see in detail. So you can recall with reference to the biasing and analyze that voltage divider biasing is best suitable for the amplification purpose. Therefore, in this common emitter configuration, we are taking voltage divider biasing. So my source side capacitance Ci, let the voltage source Vs is connected to the input having a series resistance Rs, the practical voltage source, plus VCC supply is connected, resistance R1, resistance R2. Over here I am having emitter bypass capacitor CE, emitter resistance RE, RC, output capacitance C naught, and here we will measure the output voltage V naught. So effectively in this particular circuit, we wish to analyze certain things. The first thing is what is the input impedance over here, that is my Zi. What is my output impedance over here, that is to the output port Z0. And suppose uh, effective input voltage supplied to the amplifier circuitry and corresponding the output voltage. So this is my small signal model, small signal circuit for common emitter amplifier. This is my common emitter amplifier. In fact, over here we have used NPN transistor. As far as the biasing concern, we have used voltage divider biasing. Now, for the AC analysis, we have to find its equivalent AC circuit. Okay, so we have to determine the equivalent AC circuit, and the method for that is replace capacitors by short circuit. Now the first step, and the second step, replace all DC battery, all DC batteries to the ground potential, because the purpose of biasing is just to identify the operating point. And for the amplification purpose, we should know that particular level over which the amplification will be performed. So during the AC analysis, we do not require any DC supply. Therefore, all DC supply will be replaced to the ground potential, and the capacitor will replace by an short circuit, so that the input signal will be connected to the amplifier. Okay, so let's see the equivalent circuit now. Collector resistance is connected between ground and collector terminal, across which we can take the output if load resistance is not connected. And as the emitter bypass capacitor is replaced by a short circuit and it comes in parallel to the emitter resistance, so practically entire current will flow through this. Therefore, we have marked short circuit over here, and these two resistances R1 and R2 now become in parallel, so we have placed that across which the effective input voltage will appears, and the source resistance, the practical source, is connected over here. So this is my AC equivalent circuit. Interesting part over here is you can check, we have highlighted this transistor in a box. So depending upon a particular model which we want to use for the analysis of the amplification, we can use, like I have mentioned in the previous note, there are three possible models: RE model, hybrid model, or hybrid pi model. So in this course, uh, let's use this RE model for the analysis of the transistor. Okay, so let's see the RE transistor model for common emitter amplifier. As we have taken the example of common emitter case, therefore we are discussing for common emitter. However, one can calculate the same for common base and common collector also. Okay, base terminal, it will have the input current II, collector terminal is my output terminal which provides the output current, and this is my emitter terminal which is grounded. So this is a simple common emitter amplifier circuit. You can notice we have marked the small current notation for the AC analysis. So in general, the capital letters we are using for current for the DC analysis. However, the small letters of notations we are using for the AC analysis. And its equivalent RE model is like this. So it will include one dependent source, which is current dependent current source, and one diode. So here the significance of diode is important. You can check for the amplification purpose. We kept one condition, that is my emitter junction should be forward bias. So this is the analogy, that we are taking that particular junction as a diode which is forward biased, and uh, assuming that the resistance of that particular diode is Re when it is forward biased. So just because of that, it is termed as my Re model. And this is my output current. So IC, and you can check the typical value of IC is beta times of IB, where my IB is the input current. So I'm saying that my effective input voltage is Vi over here, and output voltage which we are measuring across the collector is V naught. So this is my equivalent RE model for the transistor. Equivalent RE model for the transistor. And in general, for amplification purpose, we are interested in the following terms. What is the input impedance of the amplifier? What its output impedance? What is the voltage gain? And what is the current gain? So for this particular model, let us use the RE model and let us find the respective formulas. Okay, so let us find the term. In fact, can use certain basic terms. If you can recall, we have used IC equals to beta times of IB and current IE equals to 1 plus beta times of IB. So if I'm considering for the situation if beta is much greater than 1, then in that situation emitter current can also be approximated as beta times of IB if above conditions is satisfied. Now from this particular circuit you can check over here there is my input impedance, and input impedance can be defined as the ratio of input voltage to the input current. So my input impedance Zi can be defined as Vi upon input current Ii. So effectively, if you can check my input voltage is voltage between base and emitter, that means I can term as this is my VBE divided by input current IB, and input voltage VBE is nothing but this VBE input voltage is voltage across the diode when it is forward bias. So I'm saying that if Re is the resistance of diode when it is forward bias multiplied by the current flowing through that, and as this is the emitter terminal, so current flowing through this will be emitter current IE. And now I can replace the value IE by beta times of input current, that is my current IB. Therefore, my overall input impedance of the amplifier is Re into beta times of IB divided by I. So IB will be cancelled out. We are having interesting relation. My input impedance equals to Re into beta for common emitter amplifier. For common emitter amplifier using RE model. Now at the same time we can also find the value of output impedance, and usually the typical value of this component is infinite ohm for RE model. When we can calculate the value of R naught as from the slope of the output curve. Slope of the output curve for different input currents. So depending upon the value of currents, one can easily find the slope of the output curve, and from that one can calculate this value. But usually for this RE model, the typical value of Z naught is infinite ohm. That means it will use as an open circuit. This is my input impedance, so represented by beta into Re. Current flowing over here is input current IB. Effective input voltage Vi. So this is my RE model. This is my RE model for common emitter configuration. And in order to find the voltage gain, in order to find, so my voltage gain AV will be equals to output voltage V naught upon Vi, and you can check my V naught. So let us determine the value of V naught first. V naught is the direction is reverse for current, so it is minus times of IC into RL. Okay, considering the case when R naught is open circuit, and put the value of IC so that we can have the value of input current, so it is minus beta times of IB into RL, and you can check what is the value of input voltage. This is nothing but the drop across here, so my input voltage is beta times RE into input current IB. Therefore, my voltage gain AV equals to now minus beta times IB into RL divided by beta times RE into input current IB. You can check this IB and beta. These will be cancelled out. Therefore, my voltage gain is minus load resistance RL divided by diode resistance small r. So this is my voltage gain for common emitter amplifier using RE model. And the last component now is my current gain. So it will be AI. This is output current upon input current I naught divided by current IB. Uh, in fact, we have taken this current I naught as IC, so I'm writing directly current IC upon IB, and you can check this ratio IC upon IB is termed as beta. So my AI equals to beta. That is my forward current gain for common emitter amplification. Okay, so these are the four components. In fact, I am summarizing over here to which we are interested. Input impedance, which is my beta times of RE. Output impedance, usually infinite, or it is equivalent to R naught. So in fact, I am rewriting by including both the parameters where R naught can be calculated from the characteristics or from the design data sheet of that particular transistor. So it is R naught or infinite for RE model. My voltage gain AV equals to minus external load resistance divided by RE, and my current gain AI is nothing but beta, or it is known as HFE, forward current gain. So these are the parameters which we require for the small signal analysis for a common emitter amplifier. Okay, now let us discuss one small numerical. So, determine the value of ZI, AV, and AI if values are given as beta is given as 150 and emitter current IE is given as 3.2 milliampere. A load resistance RL of value 2 kilo ohm is connected such that the value of R0 is given as infinity. So for this database, we have to solve the problem. So it's a general problem, and let's explore the solution. So it's directly formula based. We have to first determine the value of Re, and it is my, so nothing is given, so assuming that the room temperature condition is there, and as room temperature is given, that means Vt divided by IE is nothing but Vt is my 26 millivolts divided by IE is 3.2 milliampere. So let me rewrite this. Vt is nothing but Kt by Q. In earlier module, we have discussed where K is my Boltzmann constant, T is temperature in Kelvin, and Q is the charge on electrons. So if you put all these values, so at room temperature, this value will be of 26 millivolt at room temperature. So you can verify this. We have already given the solution of the same. Now, on putting all such values, the outcome is value of resistance Re is my 8.125 ohm, 8.125 ohm. So now one can easily calculate the input impedance Zi. This will be my beta times of Re. So beta is given as 150 multiplied by 8.125, and the value of input impedance is 1218.75 ohm. So this is one component. Now we can easily calculate the value of voltage gain AV, which is my minus times of RL upon RE. So minus 2 into 10 raised to the power 3 divided by 8.125. So value of voltage gain is my minus 246.15, and my Z naught will be equals to R naught will be equals to infinity, and the last, the current gain AI equals to beta, which is directly given 150. So these are the components, these are my results for given problem. My value of RE is 8.125. So with this is my input impedance and this is voltage gain. Now let us discuss the frequency response. So depending upon the type of signal which we are analyzing, uh, lower frequency or mid to high frequency, we have to draw the response as per the analysis of my transistor. So as we have limited the discussion for the small signal analysis or for lower frequency. So in this frequency response, we will keep continue and we will see the response of transistor as an amplifier for low frequency analysis. For low frequency analysis. So for this, we are starting the discussion with a basic circuit of RC. It's a sort of series combination. I'm taking C as a capacitance and R resistance. If input voltage VI is given over here and output measuring across the resistance. So this is my simple RC combination, or it is also termed as my simple passive high pass filter, whose frequency, the lower cutoff frequency FL, is termed as 1 upon 2 by RC, which we will drive shortly. Let's see the role of this capacitance. We know that the reactance XC is termed as 1 upon 2 by FC. So let's see the behavior of this reactance on different values of frequencies. And in fact, we are interested to check this role on extreme frequencies, that is at f equals to infinity. So you can check when f equals to infinity, that means we are talking about very high frequency. The reactance XC will be equals to 0. That means it behaves like a short circuit. I can just imagine in this situation, if this capacitance is behave like a short circuit, then whatever be the input voltage, same will available at the output. So in this situation, my output voltage will be same as the input voltage for the frequency, extreme frequency, when f equals to infinity. However, in the other case, if I'm saying that at f equals to 0, means the lowest value of frequency I'm considering over here. So if f equals to 0, you can check the value of reactance is infinity, and if it is infinity, it behaves like an open circuit. So if you can check in this network, if this capacitor behaves like an open circuit, so no current can flow through this, that means the drop across this resistance is 0. So in that situation, the value of output voltage V naught will be equal to 0. So you can check, we have seen that two frequencies we have considered, infinite and zero frequency, the two extreme corners of the frequency, and we have determined the value of output voltage from 0 to the input voltage. So we need to investigate what is the role of this particular frequency on this reactance for the intermediate level. Okay, so the general notion is, if we are increasing the value of frequency, that means the value of reactance will be decreasing. So this is the general notion. And the simple voltage division rule, if we are applying over here, then we can find the overall output voltage is nothing but the voltage across this resistance R, and it can be calculated as R multiplied by the input voltage VI divided by R plus the reactance of this particular capacitor. And this can be termed as 1 upon J 2 pi FC. As you can see that we are interested to find the value of gain. So my gain is effectively the voltage gain. AV is termed as output input voltage VI, and this will be equals to R divided by R minus J upon 2 pi FC. Or we can upgrade it. AV equals to, taking R common from here, it will be 1 upon 1 minus J upon 2 pi F into RC. So this is the voltage gain, and you can check as the frequency changes, this gain will also change. And now we are generalizing this particular term, this voltage gain, that my voltage gain AV will be equals to 1 upon 1 minus JFL upon F. Now I have taken new variable. FL is my lower frequency, and its value is 1 upon 2 pi RC. AV equals to 1 upon square root 1 plus FL over F whole square at an angle of tan inverse of FL over F, where this segment is representing the magnitude of voltage gain, magnitude of my AV, and this segment is representing the phase angle by which output voltage leads by the input voltage Vi. At F equals to FL, if my running frequency or operating frequency is equals to FL, then let us check the magnitude of AV. So at F equals to FL, my magnitude will be equals to 1 upon square root 1 plus 1 whole square. So it will comes up 1 upon square root 2, and its value is 0.707. That means at this critical value, the magnitude A becomes 70.7% to the maximum value, to its peak value of A. If one wants to calculate the magnitude in decibel, then it can be correlated as my voltage gain in decibel, and the formula is, it is termed as 20 logarithmic of base 10 my output voltage divided by VI, output voltage divided by VI, and it is simply termed as 20 log of base 10. In fact, I'm interested in magnitudes on 1 upon square root 1 plus FL upon F whole square. Okay, or we can solve it further. So this quantity becomes 20 multiplied by minus 1 by 2, and it is log of base 10 quantity 1 plus FL over F whole square. So if you are putting all the database, then this result at F equals to FL, this will come up minus 3 dB. So we are having an interesting outcome. Either this quantity is 0.707 if you are calculating in terms of ratio. Otherwise, if you are calculating in terms of dB, then it will be minus 3 dB less from the peak value. And one can draw the curve, and it will have something like that, practical curve like this. So if this is the maximum level of magnitude AV, so I'm drawing here as AV. This is my 0.707 level of AV. Over here, we will do frequency measurements in hertz, and the value of critical frequency at which gain has reduced from its peak value to the by this factor 0.707 AV. This frequency is my FL, and we have determined the value of lower cutoff frequency FL is 1 upon 2 pi RC. So this is a general notion of the frequency response. Okay, we will see later on the frequency response of common emitter amplifier for lower frequencies. Okay, thank you.